So in this video, I want to introduce some concepts relating to memory fragmentation. So let's start again with kind of our picture, right? Our picture that shows, how processes might be laid out in memory. So I have a couple of partitions here. And let's say I have, just one process running, right? That'll be the simplest thing. Let's say I'll have P0 here. And kind of for the sake of argument here, right? Let's say that P0 is not using all of the space. So let's say it's just using the top. So I'm going to kind of, sketch this in, right? The rest of the stuff there, right? Let's just assume that's not, it's not used. Okay, so we have this going on. We have kind of two types of fragmentation that can occur, right? Fragmentation is basically referring to memory that I can't use, right? That's kind of out there, right? Nobody's using it and I can't use it. Well, primarily memory that's available, right? And then the word fragmentation comes from the idea that, the memory that's available may be all over the place, right? So the first idea we have, right, is the idea of external fragmentation. So external fragmentation is basically memory across empty holes. So my external, right, is basically going to be this over here. So my external fragmentation is this stuff up here and this stuff up here. So I have memory that's available, right? That's outside of a given little area, right? So I have basically I'll label these here, right? This is area 0, area 1, area 2, right? The space outside of that of where P0 is, right? I have two spaces, 0 and 1, 0 and 2. Both those are going to be freely available memory. Those make up basically my external fragmentation. So that's how much memory kind of I have available for the process to use. And maybe right now that's fine, right? I can reuse it. I'm just kind of have to be constrained to making sure that if I have a program, right, it fits into that space that I have. So that's my external fragmentation. Call it EF. All right. The other idea we have, right, is of internal fragmentation. So internal fragmentation is a little bit different. So let's say this is internal fragmentation here. What this is referring to is this space over here. So notice in that block 0 where P0 resides, P0 is only using part of that space, right? And the rest of it, right, is unallocated. Here, right, maybe this looks something like a kind of a constant size allocation scheme, right? That's why it's so big. But that space inside of that little block there, the process doesn't use it, and basically nobody else can use it either, right? So this is kind of the worst type of fragmentation. This stuff you can't really recover from without doing some sort of rewriting. So this is what we call internal fragmentation. Okay, so we have those two kind of ideas there, right? External fragmentation is kind of open holes. The amount of memory is stored in open holes over your whole system, whereas internal fragmentation is kind of the memory that's unused inside of each process's own allocation. Okay, just to give you guys kind of a little bit of a benchmark here, right? If you're using first fit selection, right, and we won't really go into the derivation for this, right, but you're using first fit selection to pick where your programs go, well then what that means is you're probably going to lose, right, about 1/3 of your memory, right, either to external fragmentation or internal fragmentation, right. Point is, right, it's stuff that you can't, that you're not actively using, right, and maybe you don't even have a hope of using it. The issue with external fragmentation usually is that the space you have available, right, so here, where it ends up being problematic is if it's too small to fit in another process, right? Because we could have, our little partitions be very small. If they're too small, then I can't fit anybody in there, right? In which case that external fragmentation really is lost. Okay, so sometimes I can try to make things a little bit better for myself, right, by doing compaction, right? Or also defragmentation. Right? Compaction, I think, is a term in the textbook. Defragmentation is maybe a more common term. The idea, right, is that somehow I can kind of shrink things. So in this case, right, I'm actually expand my picture a little bit. Maybe we can get a better example. Let's say I add another P1 here, right? And P1 maybe just use the first half as well. So basically pretend that image there that I have, my P0 in slot 1, my P1 in slot 2, both of them are just using half of those different slots. So what I could do here, right, if I wanted to maybe clean up memory a little bit, is I could kind of, I'll have to redraw my picture. I'll put it over here. Kind of move things around a little bit, right? So I could basically say, okay, you know what? I'll have my memory divided still into thirds, right? Because that's kind of what I started with. But maybe, right, I'll basically move P1 up, right? So I got P0 here, P1 here. And in this case, right, I don't have any internal fragmentation anymore, right? I'm taking P1 and putting it in the space by P0. So that's kind of a nice thing to do because then all of a sudden I don't have that internal fragmentation anymore, right? I just have these things back to back, right, and I have more uses of my memory. So that would be kind of a compaction operation, right? If I'm shifting things to get them back to back. So a couple of notes here real quick is, first of all, right, I can only do this, right, when my programs are basically set up to be stored at any address, right? In some older operating systems, right, maybe it forces it, right, and I can only store it at a certain position. Here we need to have programs, right, that are ready to be moved around. The second thought, right, is that we can only do compaction on programs, right, that don't use I/O, right, or are not, active in I/O calls. Maybe take 1 second to think about why. Why might that be the case? So the reason we don't want to do that is because if I make an I/O call, typically what happens is I give the I/O call like an address, like once you're done, store the memory, store what you got here. You can think of that like in scanf, right? Scanf takes an address, it's the address of where you should put the result. Well, if I make an I/O call and then move the program, basically that I/O device, right, will be left thinking that it needs to store something at that old address. But that old address is with respect to the program's original position, not to the program's new position. And so it gets confused, right? It'll end up writing to a position that it is not belongs to that program anymore. And so it doesn't make sense, right? So if somebody else basically is expecting to give you information back at a certain address, we don't want to move you, right? Because then that person won't be able to return the data to the right place. So that's kind of our other constraint. So there you have it, guys. That's kind of an overview of the ideas of memory fragmentation.